This is an impossible journey together, one that will take us through layers of rock and fire, through realms of pressure so intense they would crush us instantly, into a world that exists right beneath our feet, yet remains more mysterious than the surface of Mars. What would it actually feel like to travel to the center of the Earth? Not the romanticized version from Jules Verne's imagination, but the real, visceral, terrifying experience of descending through nearly 4,000 miles of our planet's hidden depths. It's a question that has captivated human curiosity for centuries, and tonight we'll explore every sensation, every impossible challenge, every breathtaking wonder you would encounter on this ultimate journey into the heart of our world. If you find comfort in these gentle explorations of our natural world, I'd be grateful if you'd consider subscribing and liking this video. The visuals are here for you, but feel free to close your eyes, breathe deep, and let your imagination descend with us into the planetary depths. There's absolutely no problem if you drift off during this exploration. Before we begin our descent, I'd love to know where you're listening from tonight. Feel free to comment your time and location below. Now, imagine standing at the edge of what would become the deepest hole ever conceived. Not the modest 12 kilometers of Russia's Kola super-deep borehole, but a shaft that plunges all the way through our planet's heart. As you peer into this impossible opening, you're looking at a journey of 6,371 kilometers straight down. To put that in perspective, if you could drive this distance on the surface, you could travel from New York to Rome and still have distance left over. But this isn't a horizontal journey across familiar landscapes. This is a vertical plunge through realms of our planet that have never known sunlight, through pressures that exceed anything in our surface experience, through temperatures that rival the surface of the sun itself. Every meter of this descent would reveal new wonders and new terrors, each layer of our Earth telling a different story of geological time and planetary formation. The first thing you would notice as you begin your impossible descent is how quickly the familiar world disappears above you. Within just a few hundred meters, the last traces of natural light would fade, leaving you in a darkness more complete than any cave system on Earth's surface. But this darkness isn't empty. It's alive with the subtle sounds of settling rock, the distant whisper of groundwater finding its way through microscopic cracks, the barely perceptible groaning of the Earth's upper layers responding to pressures far below. The temperature at this shallow depth would still feel relatively comfortable, perhaps matching a cool spring day on the surface. But with every meter you descend, you would feel the gentle but relentless increase in heat. This isn't the dry heat of a desert or the humid warmth of a tropical climate. This is the deep, penetrating warmth of a planet that has been generating heat for over 4.5 billion years. The accumulated energy of radioactive decay and the leftover heat from Earth's violent formation still radiating outward from its core. As you pass through the first few kilometers, you would encounter the shallow groundwater systems that sustain life on the surface above. Here, water moves through networks of connected spaces in rock and soil, carrying dissolved minerals and nutrients that support entire ecosystems. You might notice the subtle change in air pressure as you move through these water-saturated zones, feeling the humidity increase and decrease as you pass through different geological formations. The rock walls around you would tell the story of Earth's recent geological history. Layers of sedimentary rock formed over millions of years from the accumulated debris of ancient seas and river systems, would display their bands of color and texture like pages in a massive book. Each stratum represents a different chapter in our planet's past, containing fossils and mineral formations that speak of climates and conditions vastly different from today's surface world. But these familiar rock types wouldn't last long on your journey. As you descend deeper, passing through 10, 20, 30 kilometers beneath the surface, you would begin to encounter the true basement of the continents. Here, the sedimentary layers give way to much older rocks. Crystalline formations that were forged in the intense heat and pressure of Earth's early history. These are the ancient granites and gneisses that form the stable cores of our continents. Rocks that have remained largely unchanged for billions of years. The pressure around you would be increasing dramatically now. At 30 kilometers depth, the weight of all that rock above would create pressures nearly 1,000 times greater than what you experience at sea level. If you could somehow maintain your human form on this journey, you would feel this pressure as an all-encompassing squeeze, like being wrapped in an invisible blanket that grows tighter with every passing meter of descent. The temperature, too, would be climbing relentlessly. At these depths, you would be experiencing heat comparable to the interior of a pizza oven, hot enough to begin affecting the structure of familiar materials. Water, if it existed at these depths, would be superheated far beyond its normal boiling point, held in liquid form only by the immense pressure surrounding it. As you continue your descent, approaching the 50-kilometer mark, you would cross one of the most significant boundaries in our planet's structure, the transition from the continental crust to the mantle beneath. This isn't a sharp line like the surface of the Earth, but rather a gradual transition zone, where the composition and properties of rock change dramatically over just a few kilometers of depth. Here, you would encounter your first taste of the mantle, that vast layer of hot, dense rock that makes up the majority of our planet's volume. The familiar granites and sedimentary rocks of the crust would give way to peridotite, a dark, heavy rock rich in iron and magnesium. This rock, formed under conditions of extreme heat and pressure, represents the primary building material of planetary interiors throughout our solar system. The sensation of entering the mantle would be unlike anything in human experience. The pressure would now exceed 10,000 times that of Earth's surface, while temperatures would soar beyond 500 degrees Celsius. At these conditions, the very concept of solid and liquid begins to blur. The rock around you wouldn't be molten in the way we typically think of lava, but it wouldn't be solid in any familiar sense either. Instead, it would exist in a state somewhere between the two, capable of flowing like a viscous liquid over geological timescales while maintaining many properties of a solid material. You would begin to notice something remarkable about the rock at these depths. Despite the extreme conditions, it would possess an almost crystalline beauty. The minerals that make up mantle rock form under such perfect conditions of pressure and temperature that they create structures of stunning geometric precision. Olivine crystals, pale green and perfectly formed, would catch whatever light source you carried, creating an otherworldly landscape of natural architecture. The sounds of the deep earth would become more apparent here. The constant settling and adjustment of rock under pressure would create a subtle symphony of creaks, groans, and occasional sharp cracks as minerals adjust to the changing conditions. This isn't the violent noise of earthquakes or volcanic eruptions, but rather the quiet, persistent sound of a planet continuously reshaping itself under its own immense weight. As you descend through the upper mantle, passing 100, 200, 300 kilometers beneath the surface, you would begin to experience one of the most remarkable features of our planet's interior: convection. The rock around you, despite its apparent solidity, would be moving, Not quickly by human standards, but over millions of years. This hot mantle rock rises from the deep interior, cools as it approaches the surface, and then sinks back down in vast, slow-moving cycles that drive the motion of continents and the formation of ocean basins. You might sense this motion as a subtle current in the rock around you, like being suspended in an incredibly thick, slow-moving river. The temperature gradients that drive this convection would create zones of slightly different heat, and you might notice how the rock composition changes subtly as you move through different parts of these vast convection cells. At these depths, the pressure would exceed 30,000 times that of Earth's surface, while temperatures would climb beyond 1,000 degrees Celsius. The rock around you would glow with its own heat, creating an eerie, red-orange illumination that would make artificial light sources unnecessary. This isn't the bright, flickering glow of fire, but rather the steady, intense radiance of matter heated to temperatures that transform its very nature. The minerals around you would be unlike anything found on Earth's surface. The extreme pressure would force familiar minerals into new crystalline structures, creating compounds that can exist only in these deep conditions. Diamonds, those precious gems that form in the upper mantle and are brought to the surface by volcanic eruptions, would become more common as you descend, though at these depths they would be just another mineral among many, their surface rarity meaningless in the high-pressure world of the deep Earth. As you continue your impossible journey, approaching the 400-kilometer mark, you would encounter one of the most significant transitions in Earth's interior, the boundary between the upper and lower mantle. Here, the pressure becomes so intense that it fundamentally changes the way atoms arrange themselves in crystalline structures. The olivine and pyroxene minerals that dominated the upper mantle would transform into denser forms with the same chemical composition, but radically different properties. This transformation zone would represent a milestone in your journey, marking your passage into realms of our planet that are truly alien to surface experience. The pressures here would exceed 50,000 times atmospheric pressure, while temperatures would soar beyond 1,500 degrees Celsius. At these conditions, matter behaves according to rules that have no parallel in our everyday world. The sensation of crossing into the lower mantle would be profound. The rock around you would become noticeably denser, and the subtle currents of convection would change character, as the transformed minerals create new patterns of flow and movement. The glow of heated rock would intensify, creating an environment bathed in steady, orange-red light that reveals the alien beauty of these deep formations. Here in the lower mantle, you would truly be in a world unto itself. This vast layer, extending from 400 kilometers depth all the way down to nearly 3,000 kilometers, contains more rock than all the surface features of Earth combined. It's a realm of slow-moving currents and patient transformation, where individual crystals might exist unchanged for millions of years while participating in the grand cycles that shape our planet's surface. The journey through the lower mantle would reveal the true scale of our planet's interior. Kilometer after kilometer of hot, dense rock would pass by, each depth revealing subtle variations in composition and structure, while maintaining the overall character of this deep realm. The pressure would continue its relentless increase, the temperature would climb steadily higher, and the sense of being in an utterly alien world would grow with every passing meter of descent. As you approach the deepest reaches of the mantle, nearing the boundary with Earth's core at nearly 3,000 kilometers depth, you would begin to sense something different ahead. The rock around you would start to show signs of interaction with an even more exotic realm below. Chemical signatures of the core would begin to appear in the mantle minerals, evidence of the slow exchange of material that occurs at the deepest boundary within our planet. This is where our journey through the first major layer of Earth's interior reaches its climax, at the doorway to the most mysterious realm of all, the core itself. But that transition and the incredible journey through Earth's metallic heart awaits us in the next part of our impossible descent. The boundary between the mantle and core represents one of the most dramatic transitions in our planet's structure. At 2,900 kilometers beneath your feet, you would encounter what geologists call the core-mantle boundary, a realm so extreme that it challenges our understanding of matter itself. Here, the familiar rock that has surrounded you throughout your mantle journey gives way to something entirely different. Liquid metal at temperatures that exceed the surface of the sun. The transition wouldn't be gradual like crossing from one room to another. Instead, you would experience a sharp, almost violent change in your surroundings. The dense silicate rock of the lower mantle would suddenly terminate, replaced by an ocean of molten iron and nickel that extends nearly 3,500 kilometers toward the center of our planet. The temperature jump would be staggering, climbing from the already extreme 1,800 degrees Celsius of the deep mantle to over 4,000 degrees at the core boundary. Imagine the sensation of crossing this threshold. The pressure, already crushing beyond comprehension at 136 gigapascals, would continue its relentless increase. But now, instead of moving through solid rock that flows like honey over geological time, you would be entering a turbulent sea of liquid metal. This isn't the calm, viscous flow of the mantle above. The outer core is a dynamic, churning mass of conducting fluid that generates Earth's magnetic field through its constant motion. The electromagnetic environment around you would become intense beyond imagination. The flowing metal carries electrical currents measured in millions of amperes, creating magnetic fields thousands of times stronger than anything experienced on Earth's surface. If you could somehow maintain consciousness in this realm, you might sense the electromagnetic forces as a strange tingling sensation, as if the very atoms of your being were responding to the massive electrical currents flowing through the metallic medium around you. The sound environment would transform completely. Gone would be the subtle creaking and settling of rock under pressure. In its place, you would hear the rushing, turbulent flow of liquid metal in constant motion. This isn't the gentle babbling of a surface stream, but rather the deep, powerful roar of a metallic ocean in perpetual circulation. Convection currents, driven by the heat flowing outward from the inner core, would create eddies and flows that dwarf any weather system on Earth's surface. The liquid iron around you would be unlike any metal you've ever encountered. Under these extreme conditions, iron behaves in ways that seem almost magical compared to its surface properties. The immense pressure compresses the atoms so tightly that the metal becomes denser than anything in our everyday experience. A cubic centimetre of this core material would weigh nearly 13 grams, making it one of the densest substances in our solar system. But the iron isn't pure. Mixed throughout this metallic ocean are lighter elements that scientists are still working to identify. Sulfur, oxygen, silicon, and other elements create a complex alloy that changes the properties of the core material in subtle but important ways. These lighter elements affect how the metal flows, how it conducts heat and electricity, and how it responds to the incredible pressures deep within our planet. As you descend through this liquid metal realm, you would notice the temperature continuing its steady climb. Every kilometre deeper brings you closer to conditions that rival stellar interiors. The The heat isn't just radiating from some distant source, it's all around you, generated by the radioactive decay of elements mixed throughout the core, and by the leftover energy from Earth's formation 4.5 billion years ago. The pressure, too, would continue its inexorable increase. At 1,500 kilometers into the outer core, you would be experiencing pressures over 200 gigapascals, more than 2 million times the atmospheric pressure at Earth's surface. Under these conditions, the normal rules of chemistry and physics that govern our surface world completely break down. Matter exists in states that have no names because they have no equivalent in human experience. The electromagnetic phenomena would intensify as you descend deeper into the outer core. The dynamo effect that generates Earth's magnetic field operates through the complex interaction of convection, rotation, and electrical conductivity in this liquid metal environment. You would be traveling through the engine room of our planet's magnetic protection system, the mechanism that shields all surface life from the harmful radiation streaming from our sun. The convection patterns in the outer core create structures that dwarf any geological formation on Earth's surface. Columnar flows of hot metal rise from the core-mantle boundary, while cooler currents descend from above, creating a three-dimensional pattern of circulation that operates on timescales of thousands of years. These aren't gentle, predictable flows like ocean currents, but rather violent, turbulent motions driven by temperature differences that would vaporize any surface material instantly. As you approach the halfway point of your journey through the outer core, nearly 2,000 kilometers below the core-mantle boundary, you would begin to sense something different ahead. The character of the flowing metal would start to change subtly, and the electromagnetic environment would show signs of interaction with an even more extreme realm below. The pressure would be approaching 300 gigapascals, while temperatures would exceed 5,000 degrees Celsius. Here, in the deepest reaches of the outer core, you would encounter some of the most dynamic processes in our planet's interior. Plumes of superheated metal rise from the inner core boundary, carrying heat and chemical signatures from the very center of our world. These thermal plumes, invisible to any surface observation but crucial to understanding Earth's evolution, represent the final stage of heat transport from our planet's heart to its surface. The interaction between these rising plumes and the overlying liquid metal creates patterns of flow that influence Earth's magnetic field for thousands of years at a time. Geomagnetic reversals, those mysterious events when our planet's magnetic poles flip positions, are born in these deep interactions between different layers of the flowing outer core. You would be witnessing the birthplace of phenomena that affect navigation systems and animal migration patterns on the surface far above. As you descend through the final kilometers of the outer core, approaching the boundary with the inner core at 5,200 kilometers beneath Earth's surface, you would prepare to cross perhaps the most remarkable transition in our planet's interior. The pressure would now exceed 330 gigapascals, while temperatures would soar beyond 5,500 degrees Celsius. At these conditions, you would be approaching the threshold where even liquid iron can no longer remain fluid. The sensation of approaching the inner core boundary would be unlike anything in your journey so far. The turbulent flow of the outer core would begin to calm as you near the interface with the solid inner core below. The electromagnetic environment would change character as the conducting liquid gives way to solid metal with different electrical properties. The very nature of heat transport would shift as conduction through solid metal replaces the convective flows that dominate the outer core. But the most remarkable aspect of approaching the inner core wouldn't be what you could sense directly, but rather what you would be witnessing in terms of Earth's deep history. The inner core, represents our planet's most recent major development, a solid sphere of iron that has been growing slowly over the past billion years as Earth continues to cool from its initial formation. Every kilometer of inner core radius represents millions of years of planetary evolution recorded in the crystalline structure of solid iron under the most extreme conditions in our solar system. The boundary itself would appear as a gradual transition rather than a sharp interface. Over several kilometers of depth, the flowing liquid metal would become increasingly sluggish as it approaches the conditions where crystallization becomes favorable. The temperature gradient would flatten as the latent heat of crystallization affects the thermal structure. The electromagnetic properties would shift as solid metal replaces flowing conductor. Crossing into the inner core would represent entering the final realm of your impossible journey, a sphere of solid iron-nickel alloy that extends 1,300 kilometers to the very center of our planet. Here, under pressures that exceed 360 gigapascals and temperatures that rival the surface of the Sun, matter exists in its most compressed and heated state anywhere in our solar system. The solid inner core isn't static despite its crystalline structure. Seismic waves passing through this realm reveal that it rotates slightly faster than the rest of our planet, completing an extra rotation every few hundred years. This superrotation, driven by electromagnetic forces generated in the outer core, means that the inner core is constantly moving relative to the mantle and crust above. The crystal structure of inner core material represents iron under the most extreme conditions imaginable. The immense pressure forces the atoms into arrangements that don't exist anywhere else in nature, creating a form of iron that is simultaneously familiar and alien. These crystals, if they could somehow be brought to Earth's surface, would instantly transform into more familiar forms of iron as the pressure released. As you descend through the inner core, approaching the center of our planet, you would be traveling through what is essentially a time capsule of Earth's formation. The innermost regions of the core contain material that has remained largely unchanged since the earliest days of our planet's existence, when gravitational collapse caused the heaviest elements to sink toward the center, during the process scientists call the iron catastrophe. The final kilometers of your journey would take you through iron that has been compressed to densities approaching 13 grams per cubic centimeter, nearly twice as dense as iron at Earth's surface. The pressure would reach its maximum at the planet's center, 364 gigapascals, over 3.5 million times atmospheric pressure. The temperature would peak at approximately 6,000 degrees Celsius, matching the surface temperature of our Sun. And then, after traveling through nearly 6,400 kilometers of our planet's interior, through realms of rock and metal that exist nowhere else in human experience, you would arrive at the center of our world. Here, at the mathematical point that represents the gravitational heart of our planet, you would find yourself in perfect balance. The mass of the entire Earth would surround you equally in all directions, creating a state of weightlessness more complete than anything experienced in space. The center of the Earth represents the ultimate destination of your impossible journey, a point in space that has never known sunlight, never felt the touch of wind or rain, never been disturbed by any surface process. It is simultaneously the most remote location in our solar system and the foundation upon which all terrestrial life depends. Every breath you take, every step you make on the surface above, is possible only because of the heat, magnetism, and geological processes that originate in these deepest realms of our planetary home. From this point of perfect gravitational equilibrium, where the entire mass of our planet surrounds you in perfect symmetry, your experience would transcend anything imaginable in our surface world. The weightlessness here wouldn't be the floating sensation of space, where gravity's pull is simply reduced by distance. Instead, you would exist in a state where every atom of Earth's mass pulls at you equally from all directions, creating a gravitational null point, more perfect than any artificially created zero-gravity environment. The temperature at Earth's center represents one of the most extraordinary achievements of planetary physics. At 6,000 degrees Celsius, you would be experiencing heat that matches the surface of our sun. Yet this thermal energy exists within solid matter compressed to unimaginable densities. The iron around you would glow with an intense, white-hot radiance that would illuminate your surroundings with the pure light of stellar temperatures contained within planetary boundaries. But perhaps the most profound aspect of reaching Earth's center would be the realization of where you truly are in the cosmic scheme. This point represents the gravitational anchor of our entire planetary system, the mathematical center around which all surface processes ultimately revolve. Every earthquake, every volcanic eruption, every movement of the continents above traces its ultimate origin to the thermal and dynamic processes occurring in these innermost realms. The journey back would present entirely different sensations and challenges. As you begin your ascent from the center, you would immediately notice how the perfect weightlessness gives way to increasing gravitational pull. Unlike the familiar experience of weight on Earth's surface, where gravity pulls consistently downward, your ascent would involve a gradually strengthening pullback toward the center you're leaving behind. The transition from inner core to outer core would feel like emerging from a solid, crystalline cave into a turbulent metallic ocean. The steady, predictable environment of compressed iron crystal would give way to the dynamic, flowing realm of liquid metal. The electromagnetic environment would shift dramatically as you move from the relatively simple magnetic properties of solid iron into the complex dynamo region where Earth's magnetic field generates through the constant motion of conducting fluid. Re-entering the outer core, you would experience the return of sound in ways that would seem almost musical after the relative quiet of the solid inner core. The rushing flow of liquid metal, the electromagnetic harmonics of vast electrical currents, the deep resonance of convection cells larger than continents would create a symphony of planetary processes that exists nowhere else in our solar system. The temperature decrease during your ascent would be imperceptible at first, dropping from 6,000 degrees to merely 5,000 degrees over hundreds of kilometers of vertical distance. But this gradual cooling would represent the beginning of your return to the thermal conditions that make surface life possible. Each degree of temperature drop, bringing you infinitesimally closer to the world of liquid water and stable chemical compounds. As you ascend through the outer core, approaching the core-mantle boundary, you would witness the great thermal engine of our planet in reverse. The heat flowing outward from the inner core would become more apparent as you move away from its source, creating temperature gradients that drive the convection patterns responsible for Earth's magnetic field. These thermal currents, invisible to any surface observation, represent one of the most important energy transfer mechanisms in our planetary system. The electromagnetic environment would gradually weaken as you approach the core-mantle boundary, though it would remain intense beyond any surface comparison. The electrical currents flowing around you, measured in millions of amperes, would begin to show the effects of interaction with the non-conducting mantle above. This interaction zone, where metallic core meets silicate mantle, represents one of the most chemically complex regions in Earth's interior. Crossing back into the mantle would feel like emerging from a metallic ocean into a world of hot stone. The pressure would remain crushing, still exceeding 100 gigapascals, but the transition from liquid metal to flowing rock would create a profound change in your sensory experience. The electromagnetic intensity would drop dramatically, replaced by the more subtle forces of gravitational attraction and thermal expansion that drive mantle convection. The lower mantle, which seemed so alien during your descent, would now feel almost familiar compared to the extreme conditions of the core. The orange-red glow of heated rock would seem almost dim after the white-hot radiance of the inner core, though temperatures would still exceed 2,000 degrees Celsius. The flowing motion of rock, imperceptible during your rapid descent, might now seem almost gentle compared to the turbulent currents of the outer core. Your ascent through the mantle would reveal the vast scale of planetary convection in ways that your descent could not. Rising currents of hot rock from the core-mantle boundary would carry you upward at speeds that, while infinitesimal by human standards, represent some of the fastest motions in Earth's deep interior. These mantle plumes, taking millions of years to complete their journey from core to surface, would provide a natural elevator through the dense rock of the lower mantle. The gradual decrease in pressure during your ascent would begin to affect the crystalline structure of the minerals around you. Compounds that exist only under extreme pressure would slowly transform back into more familiar forms, though the process would occur over vertical distances measured in hundreds of kilometers. The deep earth minerals that have never existed at surface conditions would gradually give way to compounds that, while still formed under extreme conditions, bear some relationship to surface geology. As you ascend through the upper mantle, approaching depths of just a few hundred kilometers below the surface, you would begin to encounter the first hints of surface influence. Water, that essential compound for surface life, would start to appear locked within crystal structures of mantle minerals. This water, chemically bound into rock and bearing no resemblance to surface oceans, represents one of the largest reservoirs of H2O on our planet. The temperature decrease would become more noticeable as you approach the mantle crust boundary, dropping from the extreme heat of the deep interior to the merely scorching conditions of the shallow mantle. At 1,000 degrees Celsius, rock would still glow with its own heat, but you would be entering temperature ranges where familiar chemical processes could begin to occur, where the extreme conditions that dominate the deep earth start to give way to processes that bear some resemblance to surface phenomena. The transition from mantle to crust would mark your return to the realm of familiar geology. The dense, iron-rich rocks of the mantle would give way to lighter, more varied compositions that tell the story of Earth's surface evolution. Granite, basalt, and sedimentary rocks would replace the uniform peridotite that characterizes most of the mantle, creating a more complex and varied geological environment. But even in the crust, your ascent would reveal layers of Earth's history that remain hidden from surface observation. Ancient basement rocks, billions of years old, would tell stories of planetary conditions vastly different from today's surface environment. These deep crustal rocks, formed under conditions of high temperature and pressure, would show the effects of multiple episodes of mountain building, erosion, and geological recycling that have shaped our continents over geological time. The final kilometers of your ascent would bring the first hints of surface conditions. Groundwater systems would become more apparent, carrying dissolved minerals and supporting chemical processes that bridge the gap between deep earth and surface environments. The temperature would continue its steady decrease, approaching ranges where liquid water could exist stably, where organic compounds could survive, where the chemistry of life becomes possible. As you approach the surface, the pressure would drop to levels that allow familiar physical processes to occur. Rock would behave like solid material rather than flowing fluid. Water would exist in liquid form rather than being bound in crystal structures, and the electromagnetic environment would return to the gentle conditions that allow delicate electronic processes, like those in living cells, to function properly. The transition from the deep Earth to the surface world would represent not just a change in physical conditions, but a transformation from one type of reality to another. The extreme conditions of pressure, temperature, and electromagnetic field strength that characterize Earth's interior create an environment so different from surface conditions that it might as well be another planet entirely. Emerging into daylight after your impossible journey would reveal the profound connections between surface and deep Earth that normally remain hidden from view. Every mountain range would tell the story of mantle convection and crustal recycling. Every volcanic eruption would represent material from the deep interior making its way to the surface. Every magnetic compass reading would reflect the dynamo processes occurring thousands of kilometers below. Your journey to the center of the Earth would ultimately reveal the most profound truth about our planet: that surface conditions, including the climate and environment that support all terrestrial life, are intimately connected to processes occurring in realms so remote and extreme that they challenge our ability to comprehend them. The gentle warmth of sunlight, the stable chemical environment that allows life to flourish, the magnetic field that protects us from cosmic radiation, all depend on the continued operation of planetary processes that occur in conditions more extreme than the surface of most stars. The impossible journey would leave you with a transformed understanding of what it means to live on a planet. Rather than existing on the surface of a static ball of rock, you would understand yourself as living in the outer skin of a dynamic, evolving system powered by energy sources buried so deep they might as well be in another dimension. Every breath, every heartbeat, every moment of conscious experience would be revealed as part of a planetary system that extends from the life-giving warmth of surface sunlight all the way down to the stellar temperatures and crushing pressures at our world's metallic heart. The memory of perfect weightlessness at Earth's center would remain with you as a reminder of the mathematical precision underlying all planetary processes. That point of gravitational equilibrium, where the entire mass of our world balances in perfect symmetry, represents not just the geometric center of our planet, but the focal point of all the forces that make terrestrial existence possible. And perhaps most remarkably, your impossible journey would reveal that the story of Earth's interior is far from over. Even now, as you rest safely on the surface, the deep processes you witnessed continue their ancient work. The inner core grows larger by perhaps a millimeter each year as the planet slowly cools, adding new layers of crystallized iron to its solid heart. The outer core continues its restless circulation, generating the magnetic field that will protect future generations from solar radiation. The mantle maintains its patient convection, carrying heat from the depths to power the geological processes that will shape our planet's surface for millions of years to come. In the quiet darkness of night, as you settle into contemplation of this extraordinary journey, you might find yourself listening differently to the world around you. That subtle creaking of your house settling wouldn't just be wood and metal adjusting to temperature changes, but an echo of the same forces that cause rock to flow in the deep mantle. The gentle warmth radiating from heated surfaces wouldn't just be comfort from human technology, but a reminder of the vast thermal engine operating thousands of kilometers beneath your feet. The journey to Earth's center reveals something profound about the nature of our existence. We live our entire lives on the thinnest possible skin of a world whose true character lies hidden in realms we can never directly experience. The solid ground beneath our feet, which feels so permanent and unchanging, floats like a delicate crust on an ocean of flowing rock heated to temperatures that would vaporize any surface material instantly. Consider for a moment the temporal scales involved in your imaginary descent. While your journey might have taken hours or days in your mind, the processes you witnessed operate on timescales that dwarf human experience. The convection currents in the mantle complete their cycles over tens of millions of years. The growth of the inner core represents a process that has been occurring for over 1 billion years and will continue for billions more. The heat you felt in the deep interior represents energy that has been flowing outward from Earth's core since our planet's formation 4.5 billion years ago. This perspective transforms how we understand our place in the cosmic story. We aren't just temporary visitors to Earth's surface, but participants in a planetary system whose deepest processes began before life existed and will continue long after our sun expands into a red giant. The iron in our blood was forged in the hearts of ancient stars, but it may have spent billions of years cycling through the mantle before finding its way into the biological systems that make our existence possible. The electromagnetic forces you experienced in the outer core don't just generate Earth's magnetic field, they connect our planet to the broader electromagnetic environment of our solar system. The same dynamo processes that create the aurora displays visible from Earth's surface operate through the interaction of our magnetic field with charged particles streaming from the sun. Your journey through the outer core would have taken you through the engine room of phenomena that extend far beyond our planet's boundaries. The pressure you experienced during your descent tells another remarkable story about the nature of matter itself. The same atoms that exist in familiar forms at Earth's surface transform into exotic states under the extreme conditions of the deep interior. Iron, that common metal we use for tools and construction, becomes something almost unrecognizable under the pressures of the inner core. The silicon and oxygen that make up familiar rocks reorganize into crystalline structures that have no surface equivalent. These transformations reveal that our understanding of matter based on surface conditions represents only a tiny fraction of the ways atoms can arrange themselves. The deep Earth serves as a natural laboratory for high-pressure physics, creating conditions that we can barely reproduce in our most advanced experimental facilities. Every mineral grain brought to the surface by volcanic processes carries information about pressure and temperature conditions that existed hundreds of kilometers below ground. The temperature gradients you encountered during your journey reflect the ongoing cooling of our planet from its initial formation. Earth began as a molten ball of rock and metal, heated by the energy of countless collisions during the early solar system's chaotic period. The heat you felt in the core represents the leftover thermal energy from that violent birth, supplemented by the ongoing decay of radioactive elements scattered throughout our planet's interior. This thermal evolution connects Earth's deep interior to its surface in ways that continue to surprise scientists. The heat flowing outwards from the core drives not just mantle convection and plate tectonics, but also influences the chemical evolution of our atmosphere and oceans. The volcanic gases released by deep Earth processes have played crucial roles in maintaining the greenhouse conditions that keep our planet's surface warm enough for liquid water to exist. Your journey through the transition zones between Earth's major layers would have revealed some of the most dynamic regions of our planet's interior. These boundaries aren't static interfaces, but active zones where material and energy exchange between different parts of the Earth system. The core-mantle boundary, in particular, represents a region where the chemical signatures of core and mantle materials mix in ways that affect everything from the generation of magnetic field to the composition of volcanic eruptions. The seismic waves that geologists use to study Earth's interior travel the same paths you imagine taking, but at speeds that compress your entire journey into minutes or hours. These waves, generated by earthquakes and recorded by sensitive instruments around the world, provide our only direct information about the deep Earth conditions you experienced in your mind. Each earthquake creates a natural experiment that probes the structure and properties of our planet's hidden interior. The crystals you encountered in the deep mantle and core exist under conditions so extreme that they challenge our understanding of how matter behaves. The olivine and perovskite minerals of the mantle, the iron-nickel alloys of the core, represent materials that have been compressed and heated beyond anything in our surface experience. Yet these same materials, under different pressure and temperature conditions, form the familiar rocks and metals we encounter in our daily lives. As you drift deeper into contemplation of this impossible journey, consider how the extreme conditions of Earth's interior connect to the broader story of planetary formation throughout the universe. Every rocky planet in our solar system, from tiny Mercury to massive super-Earths discovered around distant stars, likely contains similar layers of compressed rock and metal heated to stellar temperatures. The processes you witnessed during your imaginary descent operate on every terrestrial world, though with variations that reflect different planetary masses, compositions, and thermal histories. Mars, smaller than Earth, has likely cooled enough that its core no longer generates a strong magnetic field. Venus, similar in size to Earth, but with a very different surface environment, probably maintains active mantle convection, despite its hellish surface conditions. The journey to Earth's center ultimately reveals that our planet is not a passive stage upon which surface processes unfold, but an active, dynamic system whose deepest processes influence everything from daily weather patterns to the long-term evolution of life itself. The magnetic field generated in the outer core protects our atmosphere from being stripped away by solar wind. The heat flowing from the deep interior drives the plate tectonic processes that recycle carbon between the atmosphere and Earth's interior, helping to regulate our planet's climate over geological time. In the gentle quiet of evening, as you prepare for sleep, you might find yourself more aware of the vast, hidden world that exists beneath the familiar surface of our planet. The bed on which you rest sits atop thousands of kilometers of rock and metal, heated to temperatures that exceed the surface of our sun. The gravitational force that holds you safely on Earth's surface is generated by the same mass of iron and rock through which you traveled in your imagination. The journey to the center of the Earth serves as a reminder that the most profound mysteries often lie not in distant galaxies or exotic particles, but in the hidden depths of the world immediately beneath our feet. Every step you take on Earth's surface is supported by structural complexity that rivals anything in the visible universe. Every breath you take is made possible by atmospheric conditions that reflect billions of years of interaction between surface and deep Earth processes. The impossible journey reveals that understanding our planet requires thinking across scales of space and time that challenge human comprehension. The processes operating in Earth's core today began billions of years ago and will continue for billions of years into the future. The materials cycling through the mantle connect surface geology to stellar nucleosynthesis, linking the formation of our planet to the broader cosmic story of element creation in dying stars. Tonight, as you settle into rest, you carry with you the knowledge of realms that exist in perfect darkness, heated by energies older than complex life, shaped by pressures that transform the very nature of matter itself. These hidden depths, forever beyond direct human experience, form the foundation upon which all terrestrial existence depends. In understanding their alien character, we gain deeper appreciation for the remarkable conditions that make surface life possible, and for our place in the grand ongoing story of planetary evolution that connects Earth's molten heart to the gentle warmth of sunlight on your face. The center of the Earth, that point of perfect gravitational balance you visited in imagination, represents more than just a geometric location. It embodies the focal point of all the forces that make our world a living, breathing planet, rather than a cold, dead rock drifting through space. Your impossible journey there and back again serves as a reminder that the most extraordinary destinations sometimes lie not in distant realms of space and time, but in the hidden depths of the world that cradles us every moment of our lives. Tomorrow will bring new discoveries about our remarkable planet. But for now, let your consciousness drift like the slow convection currents of the deep mantle, carrying you gently through the layers of sleep while the earth continues its ancient dance around you. The memory of your journey lingers like the afterglow of stellar temperatures, a reminder that beneath the familiar world of daily experience lies a realm so extraordinary it defies imagination. You have travelled through pressure chambers that compress matter beyond recognition, through electromagnetic storms that dwarf any surface phenomenon, through temperatures that rival the hearts of distant suns. Yet all of this exists in perfect silence just beneath your feet, operating with mathematical precision that has remained unchanged for billions of years. As your breathing slows and your heartbeat settles into its restful rhythm, consider this beautiful truth. The same forces that shape iron crystals in Earth's core also guide the gentle flow of blood through your veins. The thermal energy that drives mantle convection also warms your body through the night. The gravitational field that holds our planet together also cradles you in perfect safety as you rest. You are not separate from these deep Earth processes, but intimately connected to them in ways that make every moment of your existence a miracle of planetary engineering. The electromagnetic fields generated by the churning outer core don't just protect our planet from cosmic radiation. They create the aurora displays that dance across polar skies, reminding us that Earth's hidden interior constantly communicates with the space environment around us. Every compass needle that points north responds to magnetic forces born in the metallic depths you've explored, creating a connection between human navigation and the deep dynamo processes operating thousands of kilometers below. Think about the water cycle that sustains all surface life, the rain that falls from clouds, the rivers that flow to the sea, the groundwater that nourishes plant roots, all participate in exchanges with the deep earth that operate over geological time. Water locked in mantle minerals slowly makes its way to the surface through volcanic processes, while surface water gradually descends through subduction zones to depths where it influences mantle chemistry and the generation of magmas. The carbon in your body, the calcium in your bones, the iron in your blood, all participate in grand cycles that connect surface biology to deep earth processes. Carbon dioxide released by volcanic eruptions carries chemical signatures from the mantle, while organic carbon buried in ocean sediments eventually returns to the deep interior through plate tectonic processes. The boundary between living and non-living matter becomes beautifully blurred when viewed from the perspective of planetary scale element cycling. Your imaginary descent revealed that Earth's interior isn't static, but constantly evolving. The inner core grows larger each year as the planet slowly cools, releasing latent heat that helps drive the convection processes in the outer core and mantle. Mountain ranges rise and erode over millions of years, their material eventually recycled back into the mantle through subduction zones. Ocean basins open and close over hundreds of millions of years as continents drift across Earth's surface in response to deep convection currents. These temporal scales, so vast they challenge human comprehension, provide the framework within which all geological and biological evolution occurs. The oxygen in our atmosphere, essential for complex life, accumulated over billions of years through photosynthetic processes that were made possible by stable surface conditions maintained through deep Earth heat transport. The magnetic field that protects this oxygen-rich atmosphere from being stripped away by solar wind depends on convection processes in the liquid outer core that operate continuously over geological time. The pressure gradients you experience during your journey create more than just exotic mineral phases in the deep interior. They drive the fluid motions that transport heat, generate magnetic fields, and ultimately power all of plate tectonics. The weight of overlying rock creates the conditions necessary for the phase transitions that mark the boundaries between Earth's major layers, while also providing the driving force for the gravitational separation that concentrated heavy elements in the core and light elements in the crust. Consider the remarkable precision required for Earth's internal processes to support surface habitability. If our planet were slightly smaller, it would have cooled too quickly to maintain the internal heat necessary for plate tectonics and magnetic field generation. If it were significantly larger, runaway greenhouse effects might have created Venus-like surface conditions. The size and composition of Earth's core, the thickness of its mantle, the chemistry of its crust, all fell within narrow ranges that allow liquid water to exist stably at the surface. This habitability depends not just on Earth's current internal structure, but on the way that structure has evolved over geological time. The gradual cooling of the planet has allowed the inner core to grow, changing the dynamics of outer core convection, and thereby altering the characteristics of Earth's magnetic field. These changes, in turn, have influenced the evolution of our atmosphere and the development of life itself. The journey through Earth's layers reveals the planet as a complex system where processes operating at different depths and timescales interact in ways that create emergent properties not predictable from studying any single component in isolation. The generation of Earth's magnetic field requires the interaction of thermal convection, planetary rotation, and electrical conductivity in the liquid outer core. The maintenance of plate tectonics depends on heat transport through mantle convection, the strength of lithospheric materials, and the lubricating effects of water in subduction zones. These systemic interactions create feedback loops that help maintain Earth's habitability over geological time. When volcanic activity increases, it typically releases more carbon dioxide into the atmosphere, warming the planet and accelerating chemical weathering processes that remove CO2 from the atmosphere over longer timescales. When the magnetic field weakens, more cosmic radiation reaches the upper atmosphere, potentially affecting cloud formation and climate in ways that may influence biological evolution. Your imaginary return journey from Earth's center would have revealed these feedback processes in reverse, showing how surface conditions influence deep Earth processes, just as deep processes affect the surface. The composition of oceanic crust subducted into the mantle carries chemical signatures of surface weathering processes into the deep interior. The isotopic composition of volcanic gases reflects the recycling of surface materials through mantle convection over hundreds of millions of years. The transition zones between Earth's major layers represent not just changes in physical conditions, but also regions where different types of processes interact and exchange energy and material. The core-mantle boundary is a site of complex chemical reactions between metallic and silicate materials, creating hybrid compositions that affect both magnetic field generation and mantle convection. The mantle crust boundary represents the interface between slowly convecting solid rock and the more rapid processes of surface geology and biology. These boundary regions often exhibit the most dynamic behavior in Earth's interior. Seismic studies reveal complex structures at the core-mantle boundary that may represent partially molten zones, where rising mantle plumes interact with the thermal boundary layer above the core. The lithosphere-asthenosphere boundary, while much shallower than the regions you explored in your journey, represents another critical interface, where rigid surface plates interact with the slowly flowing mantle below. The electromagnetic environment you experienced in the outer core connects Earth's interior to the broader electromagnetic environment of our solar system. Solar wind particles, guided by Earth's magnetic field, create the radiation belts that surround our planet and occasionally produce the aurora displays visible from the surface. The strength and orientation of Earth's magnetic field influence how cosmic rays interact with our atmosphere, potentially affecting cloud formation and climate over long timescales. Variations in Earth's magnetic field, recorded in the magnetic minerals of ancient rocks, provide a window into the history of core dynamics over hundreds of millions of years. Periods of frequent magnetic reversals alternate with periods of stable polarity, suggesting that the convection patterns in the outer core undergo long-term changes that reflect the thermal evolution of the deep interior. The crystalline structures you encountered in the deep mantle and core represent matter organized under conditions so extreme that they have no surface analogues. Yet these same organizational principles, operating under different pressure and temperature conditions, create the familiar minerals and rocks that form the foundation of surface geology. The olivine crystals of the upper mantle, compressed into perovskite structure in the lower mantle, represent the same chemical composition arranged according to different geometric principles imposed by varying physical conditions. These pressure-induced phase transitions don't just change the appearance of minerals, but also affect their physical properties in ways that influence large-scale planetary processes. The increased density of lower mantle minerals affects convection patterns and heat transport. Changes in electrical conductivity with pressure influence electromagnetic interactions between different regions of the interior. Variations in thermal expansion, coefficients affect how temperature changes, translate into volume changes that drive fluid motions. The temperatures you experience during your descent reflect not just the current thermal state of Earth's interior, but also its entire thermal history since planetary formation. The heat flowing outward from the core today represents a combination of primordial heat from Earth's violent formation and heat generated by ongoing radioactive decay of elements like uranium, thorium, and potassium distributed throughout the planet's interior. This thermal evolution connects Earth's deep interior to the broader story of solar system formation and the nuclear processes that occur in stellar interiors. The radioactive elements that help heat Earth's core were created in the final moments of massive stars that exploded as supernovae before our solar system formed. The iron that makes up Earth's core was forged in stellar cores through nuclear fusion processes that required temperatures and pressures comparable to those you experienced at Earth's center. The convection patterns in Earth's mantle that you witnessed operate through the same fundamental physical principles that drive convection in stellar interiors, planetary atmospheres, and the liquid outer cores of other terrestrial planets. These patterns represent solutions to the basic problem of how heat transport occurs in viscous fluids under the influence of gravitational fields, a problem that appears throughout astrophysics and planetary science. Your journey through the pressure gradients of Earth's interior revealed how the same materials can exhibit radically different properties under varying conditions. This principle extends far beyond Earth to govern the internal structure of planets throughout the universe. The rocky super-Earths discovered around distant stars likely contain the same basic materials as our planet, but compressed to even higher densities and heated to even higher temperatures in their deep interiors. The magnetic fields generated by dynamo processes in planetary cores may be common features of terrestrial worlds throughout the galaxy. The interaction between planetary magnetic fields and stellar winds creates complex electromagnetic environments around exoplanets that may influence their atmospheric evolution and potential habitability. Understanding Earth's deep interior processes provides insights into the possible internal dynamics of worlds we may never visit directly. The journey to Earth's center ultimately reveals our planet as one example of the complex systems that emerge when matter organizes itself under the influence of gravitational, electromagnetic, and thermal forces operating over cosmic timescales. The same physical principles that govern Earth's internal dynamics also operate in the interiors of other planets, moons, and even brown dwarf stars, creating a diverse family of worlds with internal structures determined by their mass, composition, and thermal history. As you settle into the peaceful rhythm of approaching sleep, carried by the gentle gravitational embrace that connects you to every atom in Earth's interior, you might find yourself listening to the subtle sounds of the night with new awareness. That distant rumble of traffic becomes an echo of the acoustic waves that travel through Earth's interior, carrying information about deep structure to seismologists around the world. The gentle settling of your house reflects the same thermal expansion and contraction processes that affect rock formations hundreds of kilometers below the surface. The warmth radiating from heated surfaces around you connects to the vast thermal engine operating in Earth's deep interior, where heat generated by radioactive decay and primordial formation continues to flow outward after 4.5 billion years. Every joule of energy that keeps you comfortable on a cold night ultimately traces its origin either to nuclear fusion in the sun's core or to nuclear decay in Earth's interior, connecting your immediate experience to the fundamental energy sources that power planetary and stellar systems throughout the universe. Your breathing, that most basic rhythm of life, participates in atmospheric cycles that extend deep into Earth's interior through volcanic degassing and the subduction of surface materials into the mantle. The oxygen molecules entering your lungs may have been released from mantle minerals during volcanic eruptions, while the carbon dioxide you exhale will eventually participate in weathering processes that transport carbon back into the deep interior over geological time. The water in your body connects you to the global hydrological cycle that extends from ocean surface evaporation to groundwater systems that penetrate kilometers into the continental crust. Some of this water participates in hydrothermal circulation systems that transport heat and dissolved minerals from the deep crust to the surface, creating the chemical conditions necessary for certain types of microbial life that may represent some of Earth's most ancient biological communities. The journey through Earth's interior reveals that the boundary between the living and non-living world becomes increasingly blurred when viewed from the perspective of planetary scale element cycling. The same atoms that participate in biological processes at Earth's surface also participate in high-temperature geochemical processes in the deep interior, moving between these different environments over timescales that range from years to billions of years. Consider how the iron in your blood connects you to the story of stellar nucleosynthesis, planetary differentiation, and ongoing geodynamic processes. This iron was forged in stellar cores billions of years ago, incorporated into the rocky materials that formed Earth, concentrated in the planetary core during the iron catastrophe early in Earth's history, and eventually returned to the surface through volcanic processes before becoming part of the biological systems that sustain your life. The calcium in your bones tells a similar story of cosmic and planetary evolution. Formed through stellar nucleosynthesis, concentrated in Earth's silicate mantle, brought to the surface through igneous processes, weathered from rocks into soil and ocean water, and incorporated into the biological structures that provide the framework for your physical existence. Every element in your body carries the history of cosmic evolution, from stellar interiors to planetary formation to the emergence of life. This perspective transforms how we understand our relationship to the natural world. Rather than being separate from geological processes, we are temporary organizations of matter that is constantly exchanging with the broader Earth system. The atoms that make up your body today were part of rocks, ocean water, atmospheric gases, and other organisms in the past, and will continue to participate in Earth system processes long after your current biological organization dissolves. The electromagnetic forces that you experienced in Earth's outer core also operate within your nervous system, though at vastly different scales and intensities. The electrical impulses that enable thought, sensation, and movement depend on the same fundamental electromagnetic interactions that generate planetary magnetic fields, though biological systems operate through the controlled movement of ions across cell membranes rather than the bulk flow of conducting fluids. These connections between biological and geological processes extend throughout Earth's surface environments. The phosphorus essential for DNA and cellular energy storage cycles through rock weathering, biological uptake, and sedimentary deposition over timescales that connect individual lifespans to the geological evolution of continents. The sulfur that helps stabilize protein structures participates in biogeochemical cycles that involve volcanic degassing, atmospheric chemistry, and the formation of mineral deposits. The journey to Earth's center reveals that understanding any aspect of our planet requires thinking in terms of connected systems operating across multiple scales of space and time. The stability of Earth's climate over billions of years has depended on feedback mechanisms that involve interactions between the solid Earth, hydrosphere, atmosphere, and biosphere. Changes in any one component can propagate through the entire system, creating complex responses that may not become apparent for thousands or millions of years. These system-level interactions create emergent properties that cannot be predicted from studying individual components in isolation. The regulation of atmospheric CO2 concentrations involves interactions between volcanic outgassing from the deep interior, weathering of surface rocks, biological photosynthesis and respiration, and the burial of organic carbon in sedimentary deposits. The maintenance of liquid water at Earth's surface depends on the greenhouse effect of atmospheric gases, the albedo of clouds and ice, and the heat transport properties of ocean circulation. Your imaginary journey through Earth's interior provides a unique perspective on these system-level interactions by revealing the deep sources of energy and material that drive surface processes. The heat flowing from Earth's interior powers not just plate tectonics and volcanic activity, but also hydrothermal circulation systems that influence ocean chemistry and support unique biological communities. The magnetic field generated in the outer core protects not just the atmosphere from solar wind erosion, but also influences the atmospheric chemistry processes that affect climate and the evolution of life. As you drift towards sleep, cradled by gravitational forces that connect you to every atom in Earth's interior, you carry with you an expanded understanding of what it means to exist as part of a planetary system. Your consciousness, that remarkable emergent property of organized matter, represents one of the most complex phenomena known to arise from the basic physical and chemical processes that govern planetary evolution. The journey to Earth's center serves as a meditation on the deep connections that link human experience to the fundamental processes that shape planetary systems throughout the universe. In understanding the alien conditions that exist just beneath our feet, we gain new appreciation for the remarkable chain of circumstances that allows complex chemistry and biology to flourish in the thin shell of moderate conditions at Earth's surface. Tonight, as you rest in the gentle embrace of our planet's gravitational field, you are participating in the ongoing story of cosmic evolution that connects the formation of elements in stellar cores to the development of consciousness in biological systems. The impossible journey you have taken in imagination reveals that the most extraordinary destinations sometimes lie not in distant galaxies or exotic dimensions, but in the hidden depths of the world that has been your home throughout every moment of your existence. Sweet dreams, fellow traveler in the cosmic depths, knowing that even in sleep, you remain connected to the vast, dynamic systems that make our living planet possible. The center of the Earth, that point of perfect gravitational balance you visited in your mind, continues its ancient work of anchoring all the forces that create the conditions necessary for consciousness to contemplate its own remarkable existence in this beautiful, mysterious universe we call home. The profound silence that would envelop you as you begin your ascent from Earth's center carries within it the weight of cosmic time itself. This isn't the familiar quiet of a peaceful evening or the hushed atmosphere of a library. This is the silence of a realm that has existed in perfect darkness for billions of years, where no sound has ever echoed except the deep, patient groaning of matter under pressures that reshape the very nature of existence. As you move away from that point of perfect gravitational equilibrium, you would feel the gradual return of weight, but not in any way your surface experience could prepare you for. Unlike the simple downward pull of gravity we know, your ascent would involve a complex dance of forces as different regions of Earth's mass begin to exert their influence unevenly. The mathematical precision of this gravitational ballet would remind you that you're ascending through the heart of a cosmic machine that has been operating with clockwork accuracy since the solar system's formation. The transition from perfect weightlessness to the subtle tug of gravitational force would occur over hundreds of kilometers, each meter of ascent adding infinitesimal weight as more of Earth's mass shifts to pull you back toward the center you're leaving behind. This gradual increase in gravitational pull would create sensations unlike anything in human experience, as if invisible hands were slowly beginning to grasp you with increasing strength. The inner core around you would continue to display its crystalline magnificence, iron atoms arranged in geometric patterns that exist nowhere else in nature. These crystals, formed under conditions that compress matter beyond surface comprehension, would catch and reflect whatever light source you carried, creating an environment that seems almost cathedral-like in its austere beauty. The hexagonal and cubic arrangements of iron atoms, locked into configurations by pressures exceeding 300 gigapascals, would create surfaces that gleam with metallic perfection. But perhaps most remarkably, you would begin to sense the subtle rotation of the inner core relative to the rest of the planet. This superrotation, driven by electromagnetic forces generated in the outer core above, means that the crystalline landscape around you is slowly turning relative to the mantle and crust far overhead. Every few centuries, the inner core completes an additional rotation compared to Earth's surface, creating a realm that exists in its own temporal rhythm, disconnected from the daily cycle of day and night that governs surface life. The temperature around you would remain at stellar levels, approaching 6,000 degrees Celsius, yet the solid nature of the inner core would create an environment strangely different from the turbulent outer core above. Instead of the rushing flow of liquid metal, you would experience the profound stability of matter locked into crystalline form by pressures that dwarf any force in surface experience. This is matter at its most compressed and organized state. Atoms squeeze together until they touch in ways that normal chemistry cannot describe. As you continue your ascent through the inner core, approaching the boundary with the liquid outer core at 5,200 kilometers from Earth's center, you would begin to sense the approach of a very different realm. The electromagnetic environment would start to change as the steady electrical properties of solid iron give way to the complex dynamics of conducting fluid above. The temperature would begin its subtle increase toward the even more extreme conditions at the core-mantle boundary. The crystal structure around you would show signs of the incredible forces that shape the inner core's evolution. Seismic waves from distant earthquakes traveling through this metallic heart would reveal that the inner core isn't perfectly uniform, but contains regions of different crystalline orientation, like a vast three-dimensional mosaic of iron crystals, each aligned according to the stress fields that existed when they formed. These crystalline domains, some larger than continents, record the history of the inner core's growth over hundreds of millions of years. Approaching the inner core boundary, you would witness one of the most remarkable phase transitions in nature. The gradual change from solid to liquid iron under conditions that exist nowhere else in the solar system. This isn't the familiar melting you might observe on Earth's surface, where ice transforms to water or metal liquefies in a furnace. This is melting under pressures so extreme that the very concepts of solid and liquid become fluid themselves. The boundary zone would extend over several kilometers of depth, a region where iron exists in a state between solid and liquid that has no surface analog. Here, the crystalline structure of the inner core begins to break down as thermal energy overcomes the ordering effects of extreme pressure. The transition would be gradual rather than sharp, like watching architectural structures slowly dissolve as their foundations shift beneath them. Crossing into the outer core would feel like emerging from a crystalline cavern into a metallic ocean in constant motion. The steady, predictable environment of solid iron would give way to the dynamic chaos of liquid metal flowing in patterns driven by thermal convection and electromagnetic forces. The pressure would remain crushing, still exceeding 300 gigapascals, but the change from solid to liquid would transform every aspect of your sensory experience. The sound environment would shift dramatically as you enter the outer core. The profound silence of the inner core would be replaced by the deep, powerful roar of liquid metal in constant circulation. This isn't the gentle babbling of surface streams or even the rushing of mighty rivers. This is the sound of metallic fluid moving in currents that dwarf any surface phenomenon, carrying more energy than all of Earth's atmospheric weather systems combined. The electromagnetic environment would intensify beyond imagination as you enter the dynamo region, where Earth's magnetic field generates through the complex interaction of flowing metal and planetary rotation. Electrical currents measured in millions of amperes would flow around you, creating magnetic fields thousands of times stronger than anything experienced on Earth's surface. If you could somehow maintain consciousness in this realm, you might sense these electromagnetic forces as a strange, tingling sensation throughout your being, as if every atom in your body were responding to the vast electrical currents flowing through the metallic medium. The temperature would continue its climb as you ascend through the outer core, approaching 5,000 degrees Celsius as you near the core-mantle boundary. This heat isn't just radiating from some distant source, but permeating the liquid metal around you, creating an environment where matter glows with its own intense thermal radiation. The outer core would be self-illuminating, filled with the orange-red light of metal, heated to temperatures that exceed most stellar photospheres. The convection patterns in the outer core would become more apparent as you ascend through this liquid metal realm. Rising plumes of hot iron, heated by the inner core below, would carry you upward at speeds that, while imperceptible by human standards, represent some of the fastest motions in Earth's deep interior. These thermal plumes, taking thousands of years to complete their journey from inner core to mantle boundary, would provide natural currents to aid your ascent through the dense metallic fluid. The chemical complexity of the outer core would reveal itself as you move through different regions of this liquid metal ocean. The iron isn't pure, but contains lighter elements that scientists are still working to identify with certainty. Sulfur, oxygen, silicon, carbon, and hydrogen create a complex alloy that changes the properties of the core material in subtle but important ways. These light elements affect how the metal flows, how it conducts heat and electricity, and how it responds to the magnetic forces generated by its own motion. As you ascend through the middle regions of the outer core, roughly 1,500 kilometers from the inner core boundary, you would be traveling through the heart of the geodynamo process that generates Earth's magnetic field. The flowing metal around you would be organized into vast columnar structures aligned with Earth's rotation axis, creating a three-dimensional pattern of circulation that operates according to principles of magnetohydrodynamics that have no surface equivalent. These convection columns, each one larger than the largest hurricanes on Earth's surface, would represent the fundamental units of the dynamo process. Hot metal rising within these columns carries electrical currents that interact with Earth's rotation to generate the magnetic field that protects all surface life from harmful solar radiation. You would be witnessing the birthplace of the aurora, the compass needle's guidance, and the magnetic storms that occasionally disrupt modern technology. The turbulence in the outer core would be unlike anything in surface experience. The Reynolds numbers that describe fluid motion in this realm exceed those of any terrestrial phenomenon, creating a state of turbulent flow that operates according to principles that challenge our understanding of fluid dynamics. Eddies and vortices in the liquid metal would form and dissipate on timescales of years to centuries, each one carrying energy equivalent to entire volcanic eruptions. This turbulent motion would create a constantly changing electromagnetic environment as the flowing metal generates and destroys magnetic field structures in complex patterns. The interaction between thermal convection, planetary rotation, and magnetic forces would create what scientists call magnetohydrodynamic turbulence, a state of matter in motion that exists in few other places in the universe. Similar conditions might exist in the convection zones of certain types of stars or in the magnetospheres of gas giant planets, but nowhere else do we find such intense magnetohydrodynamic activity occurring within a solid planetary body. As you continue your ascent through the outer core, approaching the core-mantle boundary at 2,900 kilometers depth, you would begin to sense the approach of an entirely different realm above. The chemical signatures of the silicate mantle would start to appear in the liquid metal around you, evidence of the slow chemical exchange that occurs across this most dramatic boundary in Earth's interior. Iron from the core slowly dissolves into the mantle above, while elements from the mantle are incorporated into the metallic core below, creating a complex transition zone where the chemistry of both regions intermingle. The temperature would reach its maximum in the outer core as you approach the core-mantle boundary, climbing beyond 4,000 degrees Celsius. This thermal boundary layer, where heat from the core encounters the different thermal properties of the mantle above, represents one of the most important heat transfer regions in the entire planet. The temperature gradient across just a few kilometers of depth would be steeper than anything found elsewhere in Earth's interior, creating conditions that drive some of the most vigorous convection in the entire outer core. The electromagnetic environment would show signs of interaction with the non-conducting mantle above as you approach the core-mantle boundary. The electrical currents that flow freely through the liquid metal of the outer core cannot penetrate into the silicate rock of the mantle, creating complex electromagnetic boundary conditions that affect the generation and structure of Earth's magnetic field. These boundary effects help explain some of the more mysterious aspects of geomagnetic behavior, including the occasional reversals of magnetic polarity that leave their signature in the magnetic minerals of ancient rocks. The pressure around you would begin its gradual decrease as you approach the transition from core to mantle, though it would remain at levels that exceed 130 gigapascals. This pressure, while slightly less than the crushing forces deeper in the core, would still be sufficient to compress any surface material to densities approaching that of liquid mercury. The liquid iron around you would have a density nearly 13 times that of water, making it one of the densest fluids anywhere in the solar system. The final kilometers of your journey through the outer core would reveal the complex three-dimensional structure that exists at the core-mantle boundary. Seismic studies have revealed that this region isn't uniform, but contains structures that may represent partially molten zones, chemical reaction products between core and mantle materials, or regions where the thermal boundary layer creates conditions unlike anywhere else in Earth's interior. These ultra-low velocity zones, as seismologists call them, may represent some of the most chemically and physically complex materials in the entire planet. Crossing the core-mantle boundary would represent perhaps the most dramatic transition in your entire journey through Earth's interior. The change from liquid metal at 4,000 degrees Celsius to flowing rock at 1,800 degrees would be like emerging from the interior of a star into merely furnace-like conditions. The pressure would remain crushing, but the transition from metallic to silicate composition would transform every aspect of your environment. The electromagnetic intensity would drop dramatically as you cross from the conducting outer core into the non-conducting lower mantle. The electrical currents and magnetic fields that dominated the core environment would give way to the more subtle forces of gravitational attraction and thermal expansion that drive mantle convection. The constant roar of flowing metal would be replaced by the quieter sounds of rock under pressure, creaking and adjusting to forces that operate over geological timescales. The lower mantle, which had seemed so alien during your initial descent, would now feel almost familiar after your experience in the extreme conditions of the core. The orange-red glow of heated rock would seem almost dim compared to the white-hot radiance of the inner core, though temperatures would still exceed anything in surface experience. The flowing motion of rock, imperceptible during your rapid descent, might now seem almost gentle compared to the turbulent currents of liquid metal you had just experienced. Your ascent through the lower mantle would reveal the vast scale of mantle convection in ways that your descent could not fully capture. The rising currents of hot rock from the core-mantle boundary would carry chemical signatures and heat from the deepest interior toward the surface, creating plumes that may eventually manifest as volcanic hotspots like Hawaii or Iceland. These mantle plumes, taking tens of millions of years to rise through the entire mantle, would provide natural elevators through the dense rock of the lower mantle. The mineral transformations that occur in the lower mantle would become more apparent during your ascent, as decreasing pressure allows high-pressure mineral phases to transform back into forms that can exist under less extreme conditions. The perovskite and post-perovskite minerals that dominate the deepest mantle would gradually give way to forms of olivine and pyroxene, that, while still formed under extreme conditions, bear some relationship to minerals that can be studied in surface laboratories. The convection patterns in the lower mantle would reveal themselves as vast, slow-moving currents that transport heat and material between the core-mantle boundary and the transition zone far above. These currents, operating over timescales of hundreds of millions of years, would create subtle variations in temperature and composition that affect everything from the generation of mantle plumes to the long-term evolution of Earth's surface geology. As you ascend through the lower mantle, approaching the transition zone at 670 kilometers depth, you would begin to sense the approach of different physical and chemical conditions above. The mineral phases that dominate the lower mantle would start to show signs of instability as pressure decreases, preparing for the dramatic transformations that occur in the transition zone between the lower and upper mantle. The journey through the lower mantle would take you through more than 2,000 kilometers of hot, dense rock that represents the largest reservoir of solid material in the entire planet. This vast region, containing more mass than all of Earth's surface features combined, would reveal itself as a dynamic system in slow but constant motion, transporting heat from the core to the surface and recycling material between different regions of the planet's interior. The chemical heterogeneity of the lower mantle would become apparent as you ascend through different regions of this vast convective system. Some areas would show evidence of ancient subducted oceanic crust that has been stirred into the mantle over hundreds of millions of years, while others would retain more primitive compositions that date back to Earth's earliest differentiation. These chemical variations, invisible to surface observation but crucial for understanding Earth's evolution, would create subtle differences in density and thermal properties that affect the pattern of mantle convection. The temperature decrease during your ascent through the lower mantle would be gradual but steady, dropping from over 4,000 degrees at the core-mantle boundary to perhaps 2,000 degrees as you approach the transition zone. This thermal gradient, while still representing conditions far beyond surface experience, would mark your progression back toward the realms where familiar chemistry and physics begin to operate. The pressure decrease would be equally gradual, falling from over 100 gigapascals at the core-mantle boundary to perhaps 24 gigapascals at the top of the lower mantle. While these pressures would still be sufficient to compress familiar materials beyond recognition, they would represent the beginning of your return to conditions where matter behaves according to rules that bear some resemblance to surface physics. Your ascent through the final kilometers of the lower mantle would bring you to one of the most important boundaries in Earth's interior, the transition between the lower and upper mantle at approximately 670 kilometers depth. This boundary, marked by dramatic changes in mineral structure and seismic properties, would represent your passage from the deep Earth realm of exotic high-pressure minerals into the upper mantle region, where more familiar, though still extreme, conditions prevail. The transition zone itself would represent a remarkable region where the familiar minerals of the upper mantle transform into the high-pressure phases that dominate the lower mantle. Over a depth interval of just a few hundred kilometers, olivine would transform first into wadsleyite, then into ringwoodite, and finally into the perovskite and ferropericlase that characterize the lower mantle. These transformations, driven entirely by the increasing pressure with depth, would create a region of enhanced density that affects the dynamics of mantle convection throughout the entire planet. Crossing into the transition zone would feel like entering a geological laboratory where the familiar rules of surface mineralogy bend and reshape under the patient pressure of planetary depths. Here, between 400 and 670 kilometers beneath the surface, You would witness one of nature's most elegant demonstrations of how matter adapts to changing conditions through pure structural reorganization. The olivine that dominates the upper mantle wouldn't simply disappear as pressure increases. Instead, it would transform itself, atom by atom, into denser crystalline arrangements that can withstand the growing weight above. First into wadsleyite, where the silicon and oxygen atoms reorganize into more compact configurations. Then into ringwoodite, an even denser phase where the crystal structure becomes more efficient at packing atoms into the available space. These transformations would occur gradually around you, creating a landscape where familiar green olivine crystals give way to structures that shimmer with different optical properties. The wadsleyite would display a subtle blue tint under certain lighting conditions, while ringwoodite might show flashes of deeper color that hint at its unique atomic architecture. Each mineral phase would represent the same chemical composition arranged according to different geometric principles imposed by the relentless increase in pressure. The sound environment in the transition zone would carry hints of these ongoing transformations. The steady creaking and settling that characterizes most of the mantle would be punctuated by occasional sharper sounds as mineral grains adjust to new pressure conditions, reorganizing their atomic structures in response to the changing environment. These sounds wouldn't be violent or sudden, but rather the gentle acoustic signature of matter finding new equilibrium states under evolving conditions. Water would make its presence known in the transition zone in ways that would surprise anyone familiar only with surface hydrology. Here, water molecules wouldn't exist as the familiar liquid we know, but would be incorporated into the crystal structures of the high-pressure minerals themselves. Wadsleyite and ringwoodite can incorporate significant amounts of water into their atomic frameworks, creating what geologists call nominally anhydrous minerals that actually contain more water than all of Earth's oceans combined. This hidden water reservoir would represent one of the most important discoveries about Earth's deep interior in recent decades. The transition zone minerals act like enormous sponges, storing water in forms that remain stable under the extreme conditions of the deep mantle. This water affects everything from the melting behavior of rock to the electrical conductivity of the mantle, creating a hidden hydrological cycle that operates entirely within the solid Earth. The temperature in the transition zone would continue its steady decrease as you ascend, dropping from perhaps 2,000 degrees at the bottom to 1,500 degrees as you approach the upper mantle. These temperatures, while still far beyond surface experience, would represent your continued journey back toward conditions where familiar chemical processes might begin to operate, where compounds might exist in forms that bear some resemblance to surface chemistry. The convection patterns in the transition zone would show the effects of the density changes created by mineral transformations. The increased density of the high-pressure phases would affect how heat and material move through this region, creating flow patterns that influence the entire mantle convection system. Some ascending currents from the lower mantle might stall at the transition zone boundaries, while others might penetrate through to continue their journey toward the surface. As you continue your ascent through the transition zone, you would witness the reverse transformation, as decreasing pressure allows the high-pressure minerals to revert to their lower-pressure forms. Ringwoodite would transform back into wadsleyite, then into olivine, as the atomic structures readjust to the changing pressure environment. These reverse transformations would occur just as gradually as the forward ones, creating a dynamic equilibrium where mineral phases exist at the edge of stability. The seismic properties of the transition zone would create acoustic effects unlike anywhere else in Earth's interior. The boundaries between different mineral phases would act like acoustic mirrors, reflecting and refracting seismic waves in complex patterns. If you could somehow perceive these seismic waves directly, the transition zone might seem filled with acoustic echoes and reverberations as earthquake energy bounces between the different density layers. Approaching the boundary with the upper mantle at 400 kilometers depth, you would sense the approach of more familiar geological territory. The pressure would drop below 20 gigapascals for the first time since leaving the upper mantle during your descent, while temperatures would decrease to levels where mantle rock might begin to show behavior that bears some resemblance to the flow of very viscous fluids rather than the plastic deformation that characterizes the deeper regions. The upper mantle would welcome you back with its familiar green olivine crystals, now restored to their stable low-pressure form after their transformation journey through the high-pressure phases of the transition zone. The pyroxene and garnet minerals that accompany olivine in the upper mantle would display their characteristic colors and crystal forms, creating a more varied and visually interesting environment than the relatively uniform compositions of the deeper mantle. The convection patterns in the upper mantle would become more vigorous and complex as you ascend toward regions where temperature gradients become steeper and viscosity decreases. The rock around you would flow more readily, creating currents and eddies that operate on timescales of millions rather than tens of millions of years. These faster motions would make the upper mantle feel more dynamic, more alive with movement than the patient, slow circulation of the deeper regions. Water would begin to play different roles in the upper mantle, appearing not just as a component of mineral crystal structures, but also as a separate phase that affects melting behavior and rock strength. The water content of upper mantle minerals would be lower than in the transition zone, but its effects on physical properties would become more pronounced as temperatures approach the conditions where partial melting might begin to occur. The temperature gradient in the upper mantle would become steeper as you ascend, creating more dramatic temperature changes over shorter vertical distances. This steepening gradient would reflect the transition from the deep interior, where heat transport occurs primarily through conduction, to the upper mantle and crust, where other heat transport mechanisms become important. The rock around you would still glow with its own heat, but the intensity would begin to decrease noticeably as temperatures drop below the levels where thermal radiation dominates. As you ascend through the upper mantle, approaching depths of just 100 kilometers below the surface, you would begin to encounter the first signs of interaction with surface processes. The chemistry of the rock would start to show subtle influences from materials that have been recycled from the surface through subduction zones, where oceanic crust and sediments are carried back into the mantle by the motion of tectonic plates. These recycled materials would create chemical heterogeneities in the upper mantle that affect everything from the composition of volcanic eruptions to the formation of economically important mineral deposits. Ancient oceanic crust, transformed by high-pressure metamorphism during its descent into the mantle, would contribute elements and isotopic signatures that provide clues about surface conditions that existed hundreds of millions of years ago. The pressure in the upper mantle would continue its steady decrease, dropping below 10 gigapascals as you approach the base of the crust. While these pressures would still be sufficient to create mineral assemblages that have no surface equivalent, they would represent conditions where the basic principles of familiar chemistry and physics begin to reassert themselves, where matter begins to behave according to rules that bear some resemblance to surface experience. The final kilometers of your journey through the upper mantle would bring you to the Mohorovičić discontinuity, or MOHO, the boundary between the mantle and Earth's crust. This boundary, first discovered through seismic studies in the early 20th century, would represent your transition from the deep Earth realm of dense iron-rich rock into the lighter, more chemically diverse materials that form the foundation of continents and ocean basins. Crossing the Moho would feel like emerging from a world of uniform composition into a realm of incredible chemical diversity. The dense peridotite of the mantle, dominated by olivine, pyroxene, and garnet, would give way to the lighter rocks of the crust: granite, basalt, sedimentary formations, and metamorphic complexes that record billions of years of surface geological processes. The pressure would drop dramatically, falling below 1 gigapascal for the first time in your journey. The temperature decrease across the Moho would be equally dramatic, dropping from perhaps 1,300 degrees in the uppermost mantle to perhaps only a few hundred degrees in the deepest crust. This temperature jump would represent your passage from conditions where rock flows like a viscous fluid over geological time to conditions where rock behaves as a brittle solid that can fracture and break under stress. The crust itself would reveal the complex history of Earth's surface evolution in ways that the deeper layers could not. Here, you would encounter rocks that form through processes that operate only at or near Earth's surface. Sedimentary layers created by the weathering and erosion of older rocks, igneous intrusions that formed when magma from the mantle below cooled and crystallized, and metamorphic complexes that record the effects of mountain-building events and tectonic collisions. The diversity of rock types in the crust would create a more varied and interesting environment than anywhere else in your journey. Instead of the relatively uniform compositions that characterize the mantle, you would encounter granites rich in quartz and feldspar, basalts that formed from solidified lava flows, limestone and sandstone layers that preserve the remains of ancient seas and river systems, and schists and gneisses that show the effects of high temperature and pressure metamorphism. The presence of water would become more apparent as you ascend through the crust, first as hydrous minerals that incorporated water into their crystal structures during formation, then as actual liquid water in fractures and pore spaces between rock grains. This groundwater circulating through the upper levels of the crust would represent your first encounter with the hydrological systems that support all surface life. The temperature in the crust would continue its steady decrease, approaching levels where familiar chemical processes could operate, where organic compounds could exist stably, where the conditions necessary for life become possible. The pressure would drop to levels where gases could exist as separate phases, where liquid water could flow freely through rock fractures, where the physical conditions approach those of the surface world. As you ascend through the final kilometers of continental crust, approaching the surface world that seems almost alien after your journey through the extreme conditions of Earth's interior, you would encounter the first traces of biological activity. Microorganisms living in deep groundwater systems would represent the deepest extension of the biosphere, life forms that have adapted to the high temperature, high pressure conditions that exist kilometers below the surface. These deep subsurface ecosystems would operate according to principles very different from surface biology, deriving energy not from sunlight, but from chemical reactions involving minerals and groundwater. The bacteria and archaea that inhabit these environments would represent some of Earth's most ancient life forms, possibly preserving metabolic pathways that evolved when our planet's surface was very different from today's conditions. The rock formations in the upper crust would tell increasingly detailed stories of surface processes as you approach the boundary with the atmosphere and hydrosphere. Sedimentary layers would preserve fossils and chemical signatures of ancient climates, while igneous and metamorphic rocks would record the effects of mountain-building events, volcanic eruptions, and other surface geological processes that have shaped Earth's continents over billions of years. The final meters of your ascent would bring you through soil and weathered rock into the realm of surface conditions where liquid water exists stably, where temperatures allow complex organic chemistry, where the pressure and electromagnetic conditions permit the delicate electronic processes that make life possible. The transition from the high-temperature, high-pressure world of the deep Earth to the moderate conditions of the surface would represent perhaps the most dramatic change in your entire journey. Emerging into sunlight after your impossible journey through Earth's interior would reveal the profound connections between surface and deep Earth that normally remain hidden from view. Every mountain range would tell the story of mantle convection and crustal recycling processes operating thousands of kilometers below. Every volcanic eruption would represent material from the deep interior, making its way to the surface, carrying chemical signatures from realms you have now experienced firsthand. The gentle warmth of surface sunlight would seem almost cool after your experience with the stellar temperatures of Earth's core. Yet this solar energy would represent the other half of the energy budget that drives all surface processes. The combination of solar energy from above and geothermal energy from below creates the dynamic environment that makes Earth a living, evolving planet, rather than a static ball of rock drifting through space. Your transformed understanding of Earth's interior would reveal that every aspect of surface existence depends on processes occurring in the hidden depths you have explored. The magnetic field that protects our atmosphere from solar wind erosion originates in the dynamo processes of the outer core. The heat that drives plate tectonics and volcanic activity flows outward from the deep interior. The chemical elements that make complex chemistry and biology possible were concentrated and redistributed by the differentiation processes that shaped Earth's layered structure. The impossible journey would leave you with a profound appreciation for the interconnectedness of all Earth systems, from the quantum scale processes that govern mineral crystal structures in the deep interior to the global scale circulation patterns that transport heat and material between surface and depth. Every breath you take participates in atmospheric cycles that extend deep into Earth's interior through volcanic degassing and the subduction of surface materials into the mantle. The memory of perfect weightlessness at Earth's center would remain as a reminder of the mathematical precision underlying all planetary processes, while the experience of crushing pressure and stellar temperatures would provide new perspective on the remarkable conditions that make surface life possible. The thin shell of moderate conditions at Earth's surface, which once seemed like the natural state of the universe, would now be revealed as an extraordinary and delicate balance, maintained by the complex interplay of processes operating throughout the entire planetary system. In the quiet darkness of evening, as you settle back into the familiar rhythms of surface existence, you would carry with you the knowledge that beneath every footstep lies a world more alien and extraordinary than any science fiction could imagine. The solid ground that feels so permanent and reliable floats like a delicate crust on an ocean of flowing rock heated to temperatures that would vaporize any surface material instantly. Tonight, as you prepare for sleep in the gentle embrace of Earth's gravitational field, you rest knowing that you have journeyed in imagination through realms that challenge the very concepts of solid and liquid, hot and cold, familiar and alien. The center of the Earth, that point of perfect gravitational balance, where your impossible journey reached its deepest destination, continues its ancient work of anchoring all the forces that create the conditions necessary for consciousness to contemplate its own remarkable place in this beautiful, dynamic planet we call home. Sweet dreams, fellow traveler in the planetary depths, knowing that even in sleep, you remain connected to the vast thermal engine operating thousands of kilometers below, to the magnetic dynamo that shields you from cosmic radiation, to the slow dance of mantle convection that will continue reshaping Earth's surface long after all current life has evolved into forms we cannot imagine. The journey to Earth's center reveals that we are not separate from these deep processes, but intimately part of them. Temporary arrangements of stardust temporarily organized into consciousness, briefly capable of marveling at the extraordinary world that cradles us through space and time. The profound silence that follows the completion of such an impossible journey carries with it something even more remarkable than the memory of stellar temperatures and crushing pressures. It carries the realization that this extraordinary voyage exists not just in imagination, but as a constant reality beneath every moment of your existence. Right now, as you rest in the gentle darkness, these same processes continue their ancient work in perfect silence below. Consider the beautiful irony of your position at this moment. You lie comfortably at the surface of a world whose true nature would instantly vaporize you, supported by forces so gentle they cradle you like a cosmic embrace, yet generated by conditions so extreme they rival the hearts of distant suns. The mattress beneath you rests upon foundations that extend through realms of flowing rock, liquid metal, and crystallized iron, heated to temperatures that exceed the surface of our star. Every sensation of weight, every feeling of being anchored to Earth's surface represents the cumulative gravitational pull of all that mass you have journeyed through in your mind. The 6,400 kilometers of rock and metal extending below creates the gentle downward force that keeps you safely positioned in space, that prevents you from drifting away into the cosmic void that surrounds our planetary home. The warmth radiating from your body participates in the same thermal processes that drive convection in the mantle thousands of kilometers below. The chemical energy that powers your heartbeat traces its ultimate origin to the same nuclear processes that heat Earth's interior, whether through the radioactive decay of elements forged in ancient stars, or through the primordial heat left over from our planet's violent formation billions of years ago. As you breathe in the quiet darkness, you participate in atmospheric cycles that extend far deeper than the familiar boundary between air and ground. The oxygen molecules entering your lungs may have been released from minerals in the deep mantle during volcanic eruptions that brought material from the transition zone to the surface. The carbon dioxide you exhale will eventually participate in weathering processes that transport carbon back into the deep interior over geological timescales measured in millions of years. The water in your body connects you to hydrological cycles that operate throughout Earth's entire structure. Some of this water has participated in the deep circulation systems that transport dissolved minerals from the lower crust toward the surface. Some may have been locked in crystal structures of mantle minerals for millions of years before being released through metamorphic processes, and eventually finding its way into the biological systems that sustain your life. The iron flowing through your bloodstream carries the history of cosmic evolution, from stellar nucleosynthesis through planetary differentiation to the emergence of life itself. This iron was created in the cores of massive stars, incorporated into the materials that formed Earth, concentrated in our planet's metallic heart during the great iron catastrophe of early planetary history, and eventually returned to the surface through the patient work of geological processes operating over billions of years. Your nervous system operates through electrical processes that, while vastly different in scale and mechanism, share fundamental principles with the electromagnetic phenomena that generate Earth's magnetic field in the outer core. The delicate ion flows that enable thought and sensation depend on the same basic electromagnetic forces that drive the dynamo processes, protecting our entire planet from harmful cosmic radiation. The calcium forming the framework of your bones participated in cycles that connect surface biology to deep earth geochemistry through processes of rock formation, weathering, erosion, and biological uptake that operate over timescales spanning individual lifetimes to geological epochs. The phosphorus essential for the DNA in every cell of your body cycles through weathering processes that involve the breakdown of minerals formed under high-pressure conditions in the deep crust. Each element in your body tells the story of cosmic and planetary evolution, connecting your temporary biological organization to the grand cycles of matter and energy that operate throughout the universe. You are not separate from the deep earth processes you have explored in imagination, but intimately connected to them through the constant exchange of atoms between biological and geological systems. The gravitational field that holds you gently against Earth's surface represents the cumulative effect of every atom in the planetary interior you have journeyed through, from the dense iron crystals of the inner core to the lighter silicate minerals of the upper crust. Each particle contributes its tiny gravitational influence to create the force that anchors you to this spinning world as it travels through space at thousands of kilometers per hour. The magnetic field protecting you from cosmic radiation as you sleep was generated by the same turbulent flows of liquid metal you experienced in the outer core. Those electrical currents, measured in millions of amperes and operating through convection patterns larger than continents, create the invisible shield that allows the delicate chemistry of life to operate without interference from the harsh radiation environment of space. The solid ground beneath your home floats upon the flowing rock of the mantle like a delicate raft on an ocean of material heated to temperatures that would instantly destroy any surface substance. Yet, this flowing occurs so slowly, over such vast timescales, that the surface world maintains its illusion of permanence and stability, even as it participates in the grand dance of planetary convection. The heat flowing upward from Earth's interior, imperceptible in your daily experience yet constant and substantial, contributes to every aspect of surface climate and weather. This geothermal energy helps drive the atmospheric circulation patterns that bring rain to nourish the ecosystems upon which all surface life depends. It powers the hydrothermal systems that create unique chemical environments supporting forms of life that may represent some of Earth's most ancient biological communities. The tectonic processes driven by mantle convection continuously reshape the surface world in ways both subtle and dramatic. The mountains visible on your horizon grew through the collision of crustal plates, driven by convection currents operating thousands of kilometers below. The ocean basins that separate continents opened through the same deep processes, creating and destroying seafloor in cycles that operate over hundreds of millions of years. Every earthquake represents the sudden release of stress that has been accumulating through the slow but relentless motion of rock in response to forces generated in the deep interior. Every volcanic eruption brings material from depths you have explored in imagination, carrying chemical signatures and heat from realms that exist in conditions more extreme than the surface of most stars. The crystals forming in cooling magma as it solidifies into igneous rock follow the same principles of atomic organization that create the exotic mineral phases you encountered in the high-pressure environment of the transition zone. The same physical laws govern crystal formation, whether it occurs in a surface lava flow cooling in air or in perovskite forming under pressures that exceed anything in surface experience. The sedimentary rocks that preserve the history of ancient surface environments participate in cycles that eventually return their constituent materials to the deep interior through subduction processes. The limestone formed from ancient sea creatures, the sandstone created from weathered mountain ranges, the shale deposited in prehistoric river deltas, all eventually return to the mantle, where they influence the chemistry of convection and the composition of future volcanic eruptions. As you settle deeper into the peaceful rhythms of approaching sleep, consider how your consciousness represents one of the most remarkable emergent properties of the complex planetary system you have explored. The same matter that flows in the deep mantle, that generates magnetic fields in the outer core, that forms crystals under extreme pressure in the transition zone, has somehow organized itself at Earth's surface into patterns complex enough to support awareness, memory, and the capacity for wonder. Your ability to imagine the journey to Earth's center, to comprehend the extreme conditions that exist just beneath your feet, represents an extraordinary achievement of cosmic evolution. The universe has evolved from simple hydrogen and helium created in the Big Bang through stellar nucleosynthesis and planetary formation to produce arrangements of matter capable of contemplating their own origins and place in the cosmic story. The thoughts flowing through your mind as you drift towards sleep operate through the same fundamental physical principles that govern all the processes you have explored in Earth's interior, yet somehow transcend simple chemistry and physics to create the subjective experience of consciousness. This emergence of awareness from matter represents perhaps the most profound mystery in all of science, connecting the deep Earth to the deepest questions about the nature of existence itself. Tonight, as you rest in the gravitational embrace of our planet's mass, you are cradled by forces that extend from the surface to the very center of our world. The perfect weightlessness you experienced in imagination at Earth's core represents the mathematical center of all these gravitational influences, the point around which the entire planetary system organizes itself. Every atom in your body responds to this gravitational architecture, participating in the cosmic dance that keeps our world spinning through space. The journey to Earth's center reveals that the most extraordinary destinations sometimes lie not in distant galaxies or exotic dimensions, but in the hidden depths of the world that has been your home throughout every moment of your existence. In understanding the alien conditions that exist beneath our feet, we gain new appreciation for the remarkable chain of circumstances that allows consciousness to emerge and flourish in the thin shell of moderate conditions at Earth's surface. Sweet dreams, fellow traveler in the planetary depths. Rest knowing that you are part of something magnificent and ongoing, a temporary arrangement of cosmic matter temporarily organized into awareness, briefly capable of marveling at the extraordinary world that cradles you through space and time. The impossible journey you have taken in imagination reveals that we are not separate from the universe, but intimately part of its grand unfolding story, connected through every atom to the deep processes that make our existence possible. The center of the Earth continues its patient work as you sleep, anchoring all the forces that create the gentle conditions necessary for consciousness to rest peacefully, to dream, and to wake tomorrow with renewed wonder at the beautiful complexity of this remarkable planet we call home. In the quiet darkness, you remain forever connected to the vast, dynamic systems that transform simple matter into the miracle of a living world spinning through the cosmic depths. I wish you a very good night. Hope you had an amazing time here with me in this gentle exploration through the depths of the Earth. I will see you tomorrow, as always. Until then, stay curious, keep wondering. This is Boring Science, signing off. Cheers.